Previous talk was excellent if you look at things from the business point of view. For myself, I'm a principal data scientist at PayPal, and I've been doing data science for quite a few years, still doing this. And I've started working with really big data when I joined a few years back eBay, and now at PayPal. And worked with quite a few of data sets, from behavioral data, web data, transaction data, log data, and ran project for a variety of business application and business need, including big data platform, behavioral analytics and modeling, transaction, and the combination. What I found to be one of the most promising potentials for data science and big data is the combination of disparate data sets, because the combination of them provide insight that are very hard to see if you limit yourself to a single data set, let's say a survey or transaction data, etc. If you combine it with other data sets, you can see a lot of things that you cannot see. And so just like the previous speakers say, I emphasize whole project when you start from the data and you go all the way to the delivery to the business to see what the business is doing it and measure the impact of the business. And now is the time to talk about data science and big data, because all the components are now in place. There are big data platforms. There is a lot of big data by itself to work with. And data science progressed quite a bit along the hype curve. And so it's ready to go. But the question is, what is, in fact, data science? There is still debate about that. So let's start with this. This is a selfie of a data scientist. Okay? And data scientists, there are some, but there are many opinions about this. This is just one side opinion. There are promoters of data science who think that this is the great, in fact, the quote is, the sexiest occupation for the 21st century of the next 10 years or whatever. And there are some detractors who say there isn't such a thing as data science or data scientists. And now just recently I noticed there is a new age of detractors. They say it's a commodity. The skill is now a commodity. There is software, you can go, and you don't know anything about data or data science or modeling, and you go and fit on a graphical user interface and you get a model. And I'll talk about some of those as well. But, so the question is, and I would like to look at it, is basically to look from a similar question that the previous speaker talked, what data scientists actually do and how they actually bring value. Okay? So this is just for you to remember, anybody who wants to be a data scientist. So it's great potential. Now, from 10,000 feet elevation, this is what data science is all about. You have a training set and test set, and you split, just like last speaker said, and you do performance and score, but most of the glory is given to the mid blocks, the golden blocks. Those are developing of the algorithms. Developing the algorithm, doing optimization. And you hear a lot of words like deep learning that provide some very amazing results, like image understanding, like image recognition, speech recognition, self-driving cars. And recently people have thrown in artificial intelligence in there, and they predict, no pun intended, that there are going to be robots are coming. And they are going to be smart robots. They can recreate themselves and take over the world. And this will happen between 10 to 300 years from now. Notice the variance. There is no really. But this prompted some very well-known people to advocate legal ban of this part of research. Okay. I don't think this is a real. It's just like worrying about parking place on Mars right now. We are not there yet. But in addition to those fancy, there are a lot of predictive model and data science done in all aspects of business and life, from healthcare, human resources, big data platforms, optimization, organization, healthcare, everything is there. But in addition to this to this shiny object, there are some other tasks that don't get all the glory, and if attention is not paid to them, then maybe this is the main reason project may not succeed. So let's go down to the ground level and see really what happened in data science. This is basically a lot of detailed work, a lot of work with data, and it turns out it's a very well-known statistics, and this is the counter-argument for those of you who want to be data scientists, that 80, in my opinion, 90% of your time is not in modeling and optimization. It's dealing with all those extra stuff that I'll talk about. Dealing with the data, making sure that what you create is the right stuff. This is the reality. And the reason this is important, and I'll dwell on this, is because there is a lot to be done to make sure that the model works. It's not just asking the business, but does the model take the right data, etc. So, and the objective of this detail work is to close the gap, the inherent gap between big data and predictive modeling, and machine learning if you want. And the gap is due to inherent situation where models like to get very nicely arranged data set, nice rectangular data set with nice statistical properties, enough information in the columns, enough data, but big data is the opposite of that. It is deep and wide and distributed and sparse, and some of it is not even known. A lot of it is redundant, and if you deal with real data taken from the wild, like user input, a big part of it is not even reliable. What do you know what the users put in there? Some people put data just to confuse the organization. This happens all the time. And so you have to start taking, and the data comes from a lot of sources. Big data warehouses like relational databases, Hadoop, outside, in the cloud, in the web. You take this data, you need basically to take this data, let's call it the wild data, and make sure you get it to the right side, that it can be consumed and operated upon by the model. And for this, you need to take 3 major steps. First of all, it's data exploration. And the second is, you need to make sure that the data, you heard here there are outliers, etc., and we'll talk about, it's called data munging. You know the data is flooding you, but you need to cleanse the data so that you know that the data contains the information that can be used by the model in order to make any relevant prediction. And finally, once you have the data that you cleanse, you need to make it more compact, the information more compact, and this is known as feature engineering. How you take multiple parts of the data, put them together, throw out the things that don't carry enough information, and now you get that, and this is a lot of manual work, a lot. requires tools, requires some programming, requires to do quite a bit. But once you got into this in a unified format known as data frame in the profession, and it is well understood and is statistically well behaved, then you can feed it into the model, but not just yet. The model itself needs a lot of hand holding, tuning, fine-tuning of the model. And now you have the model, and the model is right. And as the previous speaker said, is it a good one for the business? Because remember, there is an old saying that a theory can be right or wrong. A model has a third option. It can be irrelevant. So you want the model to be relevant so it can deliver results, and then it can be deployed. And this is known as validation and deployment. And all of these parts are essential into data science. They don't have to be done by a single person, but it has to be tightly coordinated. Is there? So first of all, you need to understand what the data contains. Do you know everything when you see like a set of values? Do you know what they mean from the business point of view? You see a number that's supposed to be currency. Do you know if it's in US dollar or in euro? You see time. Which time zone is it? You see, you use sometimes textual data, different languages. Can you handle the different languages? Or if you have different languages, I mean, can you understand what they say? And then when you take multiple data sets, do you have the right join keys in order to make them a coherent single data that the model requires? And then when you go, you have a lot of data. This is the big data, and you need to do visualization. So the question is, how do you visualize? Let's suppose you have 1 million data points. This chart has about 500,000 data points on it. How do you make sure that you see something rather than the blob of black dots or any color that you want? This shows a very... Okay. So now that we understood the data is understood and can be joined together, now comes, and this is basically looking at the data and trying to figure out if we understand what it is. Now comes the part that is called data munging. When we looked at the data, we identify several elements that need to be changed, and now it's time for decisions. For example, you have a lot of missing value. What do? Do you unify null symbols? There are different null symbols. Some of them say -99, some of them say all kind of funny. Model doesn't understand any of that. You have to make sure that you know what the null symbol is. And then what do you do when you have the null symbols? You sometimes, if you don't have many of them, you can impute. Otherwise, you can just discard all of those rows that have null values. But what if you have 90% null values? Throw 90% of your data set? Or maybe the good part is you have to make a lot of decisions, and every one of these decisions will impact the model and the quality of the model. For example, a lot of time when you go to different data sets, you try to join key, but you get nothing out of it, blank. Why? Because maybe on the keys, in one of them, in this very particular example, you have additional white space at the end. You look at it, you don't see anything. That's why it won't join. So you have to make sure that you can actually understand the keys and to join or to do some transformation of them. For example, if the key in one point is state and another one is county, and you want to join in it, okay, you have to map the county to a state in order to join. And we have, we need to unify value. For example, in the key, you format key or ignore the rows. You have unified value, you have money, and the time, can you make them unified? You have skewed distribution. You have, what the previous speaker wanted to show, you have very long tails. What do you do about it? You remove outliers. You transform. Sometimes you can transform it. You do log transform, and all of a sudden you have a nicely behaved distribution. A lot of time you have irrelevant or redundant values. Again, you have to make decision. Do we want to transform them, to nullify, to discard? You have to make a lot of decision here on very large data set. And this is part of the real detail work that is at the heart of the matter. The model is built on that. You can run any model you want, but if this is not well understood and well controlled, then the model will have some difficulties. Let's put it this way. Okay, now we transform the data, we have the data. Now we need to go in a lot of time to do what's known as feature engineering. And feature engineering is very important because it turns out that it's well known in data science, the better features, you have a simpler model and more accurate results. So how do you do feature engineering? There are several ways. You can do manual feature manipulation. For example, if you have dummy variables, let's suppose you have a set of multiple choices, 10 choices. What do? You can consider this 1 to 10 as a numeric, or you can go and what's in statistics, they just go and spread them and make them dummy variables. And if you have, for example, you try to do this with zip codes, all of a sudden you end up adding about 100,000 dummy variables. Not every software can handle this. So you need to know what's happening this. Some other times in manual feature manipulation, you need to do, your data set is not balanced. Like if you look at prediction, the class 1 that you want to predict may be 2%, and the rest of 0 is 98%. You run this and run any predictive model that you want, the results will not be significant, will not be meaningful. So you have to do subsampling, supersampling, in a way that preserve the statistical properties of the class that you are interested in and still give the model, because most of the models that were designed to work best when you have balanced data set. So this is something you need to understand. You as a data scientist, I refer to you as data scientist. Not all of you, but those of you who wants to be, all data scientists need to. Another thing, there are more features computational. It's called feature learning. And they are statistical. On the top left is called PCA, Principal Component Analysis. Or you can do this with metric factorization, metrics for factorization, or the hot new stuff from deep learning. You can do autoencoder. You put it in some kind of a neural network, and all of a sudden, it identifies the features inherent in the data. This is known as feature learning. You don't make your own decision. You let an algorithm decide which features are. And then, of course, you can do feature selection, manual feature selection, etc. And in some of the modeling, like this one is called the regularization. One of them is lasso. Basically selects, if you run them, the model itself selects the most important variables. But then the model basically runs on a subset of the variables. Instead of having 200 dimensions, 200 features, you end up with maybe 10 or 20, and they are more compact, deliver more information to the data. Now that you did the feature selection, now can we run the model? Not quite yet. The models today, especially in big data, requires a lot, there's a lot of tuning, a lot of, look at this is the cockpit. I have a lot of knobs, a lot of knobs you need to do. Some of them is basically parameter grids. There are a lot of parameters and different parts. So you have a set of parameters, and each one says, let's see what combination of parameters works best. So you give for every one of the hyperparameter a set of values, and now you have to run the model, the multiplication of all of this number of values. It's a lot. It can cause a lot of delay. It can run very slowly. You can take interpretability versus accuracy. For example, this is another thing you need to look at the model tuning. Do you want to take a model, like say like a decision tree, a single decision tree, that you deliver the decision tree and everybody say if, then, else, you have the set of rules, business people understand it, you go and explain, great. Accuracy is not as good as if you take a model that takes thousands of those, random forest, and run, you get better results, but people say, hey, you bring me a black box. What is better? It's, you have to make a judgment. Do you want it to work or you want to understand the details? You ask the business. This is another model tuning that you need to do. Learning rate is part of the optimization. Do you want to make it real fast or that's not that accurate, or you want to make it very slow and to go, or you want to do a stochastic gradient descent on every line? Those are a lot of decisions that you need to do. And now, ensemble is one of the magic words. You take multiple models, put them together in a big pot, you mix them all together, take the average or any combination of them, and you get a significantly better accuracy. Okay? You have to decide what kind of ensemble, what kind of degree, what type of ensemble. There are plenty of them. So even when you run the model, you have to do, and all of this is manual work. You need to go and do it manually. There will be some software to do it for you, but at the cost of running all exponential number of possibilities. If you have enough time, that's cool. Okay, we got the model tuned. So let me give you like 2 examples, not necessarily predictive modeling, part of them, yes, about how you take different data sets and come up with results that basically are meaningful to business. And you start with basically with a business question. This is one was intentionally anonymized here, but the point this is called the behavior side speed impact. People ask you, what is the impact of side speed? How much you gain if you improve famous articles by Google and by Amazon that say every 100 milliseconds will give you so much benefit, etc. Okay, so is it linear, right? So it turns out that this is a project I did based on this because people wanted to work on improving the site speed, and this takes a lot of effort and a lot of money and very big budgets and teams, and people say, why? What's in it for us? So the point is to take a data from transaction data, people who try to make payments, etc. Take behavioral data for every payment, what is the speed that they got, and join the 2 data sets. I'm saying it lightly, but it took months, a lot of effort, because those are 2 different data sets created by 2 different teams without regard to one another. And once you get that, you could see those are the dots, are particular the data points, and the blue line is the robust log regression, and strip around it is the variance, the uncertainty in the model, and the red dotted line is my manual creation in order to say to people who don't know any of that stuff, I say, you see, this is the trend. So you can interface. Yes, please.
So by combining disparate data sets, you basically are doing correlation analysis.
If I do correlation analysis?
That's the same as
yes.
combining disparate
Yes,
data sets.
yes. This is basically correlation. Although I'm inferring that this is causation. Now, and I said that this is correlation. For some, look at this is correlation. Look at all of those that have on the right, and all of those few that have on the left that were the lucky one. Correlation. You want to say this is pure choice by throwing a coin? Fair enough. Maybe, maybe not. Absolutely. I mean, I stood there and said, hey, I didn't have the means to go and say, let's take some user and do one against the other. The only way, basically reliable way, to take correlation and make sure that you know this is a causation by testing, by A/B testing, control testing. But this is a very expensive. Big data platforms, big data warehouse, and another even bigger variation, cheaper variation called singularity of the data warehouse for very large amount, petabytes of behavioral data. And we say, with a lot of replication, and I was asked, how much does it cost? Can you compare the cost to run a particular query on them, or different queries? And this is one of the results. It turns out that this was a combination of data sets. On the left, people first look at it as a TCO. The first one is the system unit cost, what's known as a TCO, total cost, ownership, cost of ownership, TCO. And Hadoop is way cheaper than the other ones. But when you go, and there was a lot of, you can find on the web, I did an analysis, you try to see what is the capacity of each one of them and how much resource identical queries take. It turns out that this is the second one, that Hadoop, they consume a much larger percentage of the capacity of the system than on the other one. And if you multiply the two, what is the cost of unit of capacity times number of capacity, turns out that Hadoop and the cheap data warehouse, which is a commercial product, are about the same. And this was run over several queries, very large queries, you know, join of petabytes of data, although the enterprise data warehouse is more expensive, but the conclusion from here was simple. Hadoop is not free. That was about it. And so this is basically an example of how you take, and this took log data from Hadoop in a totally different log data from Singularity and from EDW, combine this financial data and put this together as one result, one crisp result. Just as an example, what you can do if you know what the business is. Yes, please. Okay, the units. If you look at my name, I presented it a few years back at XLDB. It says the unit of EDW is basically CPU seconds. And this was Hadoop 1.0. It was slot seconds. Okay, and I can explain what it is. Basically, container seconds. Those are different. But it's a good point. It took some time to define what it means by capacity and how to calculate it. Okay, now you have your model, and now you have to evaluate. Is it a good model or what? Okay, I have the model. I have the results. And the first question, who is the one or the ones, who are the ones, to determine if this is a good model or not? A lot of them in the book, you'll find that people look at the combination of false positive and false negative and recall and precision and put them together and have a measure called F1, which is the overall, geometrical mean of those two, and get this is F1, this is the accuracy. Okay, that's good for data science people to argue whose model is better. But sometimes you have to look at what is the implication of FP, which is false positive, Fn is false negative, and TP is the true positive, which is the intended gain. And if you look at certain actions, let's suppose you want to see who is, whom transaction you want to block. False positive is PR cost, and people suffer of that. People send and wrote on blogs, look at PayPal, they blocked my account, they did all of this, because it was a false positive. False negative, of course, financial cost. You don't catch someone who is doing fraud, you lose money. True positive is your revenue. So who is evaluate the relative difference between them? Is just by money? For example, one thing is when you give your model, let's say the scores to people to call prospective customer to go on them. If you give those agents, they don't know what data science is, nothing. You just give them a list and say, you just go and call this. If the false positive is too high, they'll just discard them. They just won't use them. Here you know if your model works or not. Do they keep using your scores? It's important. So it's important to understand that the different performance metrics of a model the different performance metric of a model have different implication on the business, and some of this may be overwhelming. So sometimes you may emphasize precision and you don't care so much about the recall. Someone is the other way around. Okay, I mentioned before that there are now a whole set of platforms that basically provide the tools. You just go there and build your model on that. A lot of people use Python and write a lot of code, etc. This, you can go to their table there, total coincidence, total correlation, no causation. I've been working with this tool for now almost about a year, and it's a very powerful platform that has implemented distributed way a lot of machine learning algorithms with a lot of other processes. You can sit and write in R, in Python, whatever, and they have GUI that it's so sophisticated, I say it has good news and bad news. The good news is that someone who doesn't know anything about data or modeling can go there, take a piece of data, build a very sophisticated model, and get the results. That's the good news. The bad news is that someone who doesn't know anything about modeling or data can go there and create a model. So be careful about this, but it's a very impressive, it's open source, it's free, etc. And I don't have any financial interest in this company. I'm just giving you my experience with using this particular one. And so in the summary, basically, I was talking about the extra step, the steps that are around. If in the blank spot there is the model building, there are a lot of steps before and after that you have to do as a data science team, data scientist, in order to make sure that the model is acceptable, deployed, and deliver measurable result. And what you need to do for that, basically, you need to work on the details. You have to know the details. Without knowing the details, at 10K altitude, everything looks the same. And you have to make a lot of decisions there, and to have to understand the impact of the decision on the data. And you have also to make sure that what you do, the way you run, and this is a little geeky, but it's the performance of the platform. If you run the best algorithm with the best data, with big data, and it takes you 7 weeks to analyze the data that represents 1 day, it doesn't work that good. So you have to make sure that you run it effectively and you deliver the results in time that the business finds it relevant. Because if those are not, the risk here, if those principles are not adhered to, then you have delayed results, you have incomplete results, or irrelevant results, which from the business point of view, they are very similar. They just don't want to deal with them. But if you go and do the whole thing, and I apologize for the cliche, you deliver, and there is a piece of gold, and you go to the financial statement of the company and say, you see this amount, that's my model. And so this is it, but I just have to make a comment about what the previous speaker talked, and I'll skip this one. And this was from a different talk. I want to talk about, he said sometimes the past does not predict the future and all of this. There is a saying by a quote attributed to Claude Shannon, the father of information theory, who says, there is a duality between past and future and information and control. We know a lot about the past, but we can control it. We know very little about the future, but we still can do something about it. And I would like to make a variation for data science. The past may not exactly predict the future, but we analyze the past to refine our understanding so we can make informed decision about the future. And this is just my opinion about that. And then thank you.